Space exploration did not begin with rockets. It began when human beings looked up and realized the sky was not random. Ancient observers in Mesopotamia, China, Greece, the Islamic world, and later Renaissance Europe turned the heavens into a system that could be measured, predicted, argued over, and eventually tested. By the 17th century, the telescope had transformed the sky from a sacred ceiling into a physical place. By the 20th century, rocketry turned that place into a destination. The modern age of spaceflight emerged from a strange mix of dreamers, mathematicians, war machines, and state rivalry. The Cold War accelerated launch technology from missiles to satellites, then to human flight, moon landings, probes, stations, reusable spacecraft, and giant observatories. In the 21st century, space exploration became broader and more crowded. Multinational stations, Chinese lunar missions, Indian satellite landings, Japanese sample returns, commercial crew systems, and NASA's Artemis campaign all point toward a future in which the moon becomes a proving ground for Mars and beyond. At the same time, treaties, debris, planetary protection, and unequal access force a harder question. Not only can humanity go farther, but how should it go? The history of space exploration began long before launch pads. At one point in time, every human who had ever lived stood under the same sky, and no one had yet touched it. Before there were engines, there were stories. Before there were observatories, there were shadows on stone. Before there were astronauts, there were priests, navigators, poets, kings, mathematicians, and children looking upward and asking the oldest question in our history. What is out there? This is the entire history of space exploration. From the first skywatchers to the first moonwalkers, from fire arrows to liquid rockets, from Sputnik to stations, from grainy black and white images of Mars to new plans for lunar bases and future voyages to the Red Planet. For thousands of years, space was only myth, symbol, and speculation. Then very slowly it became geometry, then physics, then engineering, then at last a road. Ancient astronomy under the first sky. The first explorers of space never left the ground. They did not wear suits, sit atop rockets or speak to mission control. They watched. They memorized. They noticed patterns. A sunrise returned from the east. Seasons followed one another in order. Certain stars arrived at certain times of year. The moon changed shape in a cycle. Few lights wandered differently from the others. Those wandering lights would one day be called planets. Long before written science, the sky was a calendar, a compass, and a theatre of meaning. It told hunters when cold was coming, it told farmers when to plant, it told rulers when eclipses might terrify their people. In that sense, astronomy was never a luxury. It was survival. Humanity's first relationship with space was intimate. The night sky was not empty. It was crowded with gods, ancestors, omens, beasts, and pathways. Entire cultures built stories into constellations because stories were portable maps. They made the sky rememberable. This is where exploration begins, not with machinery, but with attention. A species that could look up, compare one night to the next, and understand that the heavens obeyed order had already taken its first step toward the stars. Stone, horizon, and time. The earliest sky watching was built into landscapes. Horizons mattered. Solstices mattered. The rising point of the sun mattered. Across the ancient world, monuments and ritual sites were aligned with celestial events, linking architecture to recurring motions overhead. These early alignments did not yet produce equations, but they produced something equally important: expectation. If the sky could be anticipated, then it could be known. If it could be known, then perhaps the universe was not merely supernatural drama, but a system. That idea changed everything. Once observation became generational, knowledge could compound. A child could inherit the sky from a parent, but with refinements. A priest could compare years of moon cycles. A ruler could sponsor specialists whose job was simply to watch the heavens and record what changed and what did not. Long before astronomy became formal science, people were conducting a kind of proto-science by repeating observations and comparing outcomes. The future of space exploration depends on this habit. Rockets, telemetry, orbital mechanics, and life support systems all emerge from a very old discipline. See carefully, write it down, test the pattern again. The first laboratories of space history were open air and silent. Their ceilings were infinity itself, Mesopotamia and the first recorded heavens. The first documented records of systematic astronomical observation emerged in Mesopotamia. Assyro-Babylonian skywatchers observed the movements of celestial bodies and recorded their periodic behaviour as early as the first millennium BCE. Their work did not yet reveal cosmic distances, but it did establish something foundational. The sky could be tracked through records, not just remembered through myth. Babylonian astronomers were masters of repetition. They tracked lunar cycles, eclipses, planetary appearances, and the regularity of celestial motion. Their tradition also helped shape the zodiacal framework that later influenced both astronomy and astrology across the Mediterranean world. The 12-part zodiac, in forms recognizable today, grew from ancient Mesopotamian systems by the end of the first millennium BCE. What mattered most was method. Once the heavens were turned into dated records, astronomy became cumulative. It could now improve over centuries. Space exploration, in its deepest sense, relies on this exact transition, from wonder to archive. And yet, these observers were not modern in the later scientific sense. Their world still united celestial motion with kingship, ritual, and omen literature. A comet could be both a physical event and a political warning, but that mixture should not mislead us. Inside it was a brilliant and durable insight. The heavens repeat in patterns, and patterns can be predicted. The future mission log was born in the clay tablet. Egypt, cycles and sacred order. Ancient Egypt also tied celestial order to earthly power. The regular flooding of the Nile, the importance of seasonal timing, and the symbolic role of the heavens meant that sky watching became deeply practical as well as sacred. Stars were not abstract objects. They participated in administration, agriculture, religion, and royal ideology. The Egyptian sky was one of alignment and repetition. Temples, monuments, and ceremonial time were linked to bodies overhead. While Mesopotamia produced the most influential early written astronomical records, Egypt helped preserve the older human refrain that the sky and civilization belong to one shared order. That idea might sound distant from spacecraft, but it is not. Space exploration has always carried cultural meaning. Launches are watched like rituals. Astronauts become national symbols. Photographs of Earth from orbit alter how people imagine politics and planethood. In that sense, the continuity is ancient. Looking upward is never only scientific. Early astronomy emerged where the practical and symbolic met. It was used to direct calendars and strengthen authority, to promise continuity in a fragile world. The stars seemed constant when kingdoms were not. Long before mission badges and agency emblems, civilizations were already turning the sky into an identity. Space was not yet reachable, but it was already shaping human civilization from above. China and the long memory of the sky. Ancient Chinese astronomy produced one of the longest continuous records of celestial observation in human history. The Chinese tradition placed huge emphasis on calendar making, observational precision, and the documentation of unusual phenomena. Official astronomers watched the heavens not only to understand seasonal cycles, but to read the condition of the political order itself. Heaven and empire were linked. Chinese records became invaluable to later science because they were so extensive. They tracked guest stars, comets, eclipses, sunspots, and planetary events over long spans of time. NASA, JPL, and Chinese astronomy institutions have all noted the value of ancient Chinese eclipse and transient object records for modern astrophysical reconstruction. One of the earliest reliably recorded appearances of Halley's Comet, for example, was observed by Chinese astronomers in 240 BCE. Centuries later, Chinese records of supernova-like guest stars would help modern astronomers connect historical observations to actual remnants in space. China also built observatories and instruments long before telescopes. Astronomical watching was embedded inside governance. Skilled observers were expected to keep a constant watch over the sky because celestial irregularities could be interpreted as messages of disorder. This is one of the oldest recurring themes in space history. The sky is never neutral. It is scientific data, yes, but also meaning. That was true in ancient China, and in a different way it remains true whenever a launch becomes a matter of national prestige. India, cosmology and mathematical sky, across South Asia, traditions of astronomical thinking also developed in close relation to calendars, ritual timing and mathematics. The sky was studied not simply as a visual world, but as a numerical one. Timekeeping, eclipse prediction and planetary cycles mattered deeply in both ritual and scholarly contexts. What matters for the long history of space exploration is that astronomy became increasingly mathematical across several ancient civilizations at once. The transformation of the heavens from symbolic narrative into computable motion did not happen in one place or with one people. It was plural, it was cumulative, it was transmitted, translated, argued over and reworked. This broader truth matters because modern spaceflight often gets narrated as though history begins in one 20th century rivalry. In reality, the launch era rests on millennia of global sky knowledge. No rocket reaches orbit without mathematics, and no civilization arrives at celestial mathematics overnight. By the time the modern age began, humanity had been building conceptual ladders to the heavens for thousands of years. Some were mythic, some were geometric, some were observational. Together, they formed a kind of long runway. The modern rocket would be spectacular, but its deepest roots lay in patient civilizations teaching themselves that the sky had rules. Greece and the geometry of the cosmos. The Greek world added a decisive new ingredient: geometry as a language of the heavens. Earlier observers had tracked cycles. Greek thinkers increasingly sought models. What shape was the world? What moved around what? Could celestial order be described in coherent mathematical form? Greek astronomy did not appear from nowhere. It drew on older observations, especially from Mesopotamia, but it changed the style of explanation. This was not only record-keeping, it was theorizing. Why do the planets wander? What is the structure of the cosmos? Is Earth central, or is our perspective deceptive? By the 2nd century BCE, Hipparchus compiled what ESA describes as the oldest known comprehensive catalogue of stellar positions. His work was based in part on even older Assyro-Babylonian observations, and would later be transmitted through Ptolemy's Almagest, one of the most influential astronomical texts in history. Greek astronomy left behind more than numbers. It left behind a habit of asking whether appearances told the truth. The sun seems to move, the stars seem fixed, Earth feels still, but is seeming the same as reality. That question sits close to the heart of every later space breakthrough. Orbit itself depends on abandoning surface intuition. Space history is filled with moments when the universe turned out to be less like common sense and more like mathematics. Greece helped train humanity for that shock. Ptolemy and the endurance of Earth-centered space. Claudius Ptolemy, writing in the 2nd century CE, did not invent geocentrism, but he gave it one of its most powerful and durable formulations. In the Ptolemaic system, Earth sat at the centre, while planets, the sun and the stars moved around it through an elaborate set of circular motions. This model could become extremely complicated, but it worked well enough as a predictive system to dominate learned astronomy for centuries. This matters because space exploration is not only a story of machines, it is also a story of mental imprisonment and release. The Ptolemaic cosmos was elegant, stable and deeply intuitive. It matched how the sky seems to behave from the ground. It also placed humanity in the middle. The later destruction of that picture would be emotionally and philosophically enormous. It would force human beings to accept that Earth might not be the centre of anything. In a strange way, the psychological difficulty of space exploration begins here. To go into space, humanity first had to stop imagining itself as the still point of the universe. For more than 1,000 years, Ptolemy's framework shaped educated understanding of the heavens. That durability reminds us of an important truth. Wrong models can still be incredibly useful, and scientific revolutions often emerge by stretching older systems until they begin to crack. The first great crack was already on its way. The Islamic world and the refinement of the heavens, between late antiquity and the European Renaissance, the Islamic world became one of the great crossroads of astronomical knowledge. Classical works were translated, critiqued, corrected, expanded, and instrumentally refined. Astronomers across the Islamic world improved observational methods, built instruments, and developed mathematical tools that later shaped European astronomy. Smithsonian scholarship notes that Islamic astronomers identified problems in Ptolemy's planetary hypothesis as early as the 10th century and developed refined mathematical approaches that were later taken up in Europe. Astronomical instruments tell the story with special clarity. Astrolabes, celestial globes, observational tables, and star traditions moved through Islamic scientific culture with great sophistication. The British Museum notes that medieval English astrolabes themselves show the influence of Arabic astronomy and instrumentation. This era matters because the line from ancient astronomy to modern science was not a simple relay from Greece to Europe. It was a braided history of transmission and transformation. Texts crossed languages, instruments crossed empires, problems were inherited and improved. Without this intermediate world of scholarship, the later astronomical revolution in Europe would have been thinner, slower, and poorer. Space exploration eventually became a global endeavour. In a deeper sense, it always had global foundations. The sky had many interpreters before it had astronauts. Copernicus and the dangerous rearrangement of reality. In 1543, Nicholas Copernicus published a full heliocentric theory in which Earth orbited the Sun. The Library of Congress describes this as a landmark publication that set forth evidence for a sun-centred system and laid the basis for the later work of Kepler, Galileo, and Newton. What Copernicus changed was not merely astronomy. He rearranged dignity. He removed Earth from the centre and turned humanity into inhabitants of a moving world. This was more than a scientific adjustment. It was a civilizational insult to common sense. At first, heliocentrism did not instantly win because it did not yet explain everything more cleanly than the older system. But it opened a new possibility. Perhaps the cosmos made better sense when viewed from outside Earth's immediate intuition. That shift would become fundamental to all later space science. Orbital mechanics, planetary motion, interplanetary navigation, and modern astrophysics all begin with the idea that Earth is one world among others, not the floor of creation. Copernicus did not launch anything. He launched a perspective, and perspective is often the first stage of exploration. Before anyone could send a probe to another planet, someone had to imagine planets as places moving through a shared system around a star. Heliocentrism made the solar system thinkable as a destination map. A rocketless revolution had begun. Tycho, Kepler, and the shape of motion. The Copernican idea needed evidence and refinement. Tycho Brahe spent years making exceptionally precise observations of the sky. Johannes Kepler inherited that observational treasure and transformed it into laws of planetary motion. Circular perfection gave way to ellipses. Planetary orbits were not idealized divine loops. They were mathematical paths with structure. The importance of Kepler cannot be overstated for the history of space exploration. Spacecraft trajectory design lives inside a Keplerian universe. Transfer orbits, slingshots, lunar insertion, and interplanetary cruise all depend on the fact that motion through space is lawful and calculable. In a sense, Kepler made the solar system navigable centuries before there was navigation technology to exploit it. His work also marked a methodological victory. Observation and mathematics had joined forces against inherited aesthetics. The universe was not obliged to be simple in the way philosophers preferred. It only had to be true. This was a profound liberation. Space would not be reached by reverence. It would be reached by correct equations. Exploration histories often celebrate engineers at Cape Canaveral or Baikonur. They deserve it. But the launch pad also extends backward to Brahe's patient records and Kepler's stubborn analysis. Before there were rockets aimed at the moon, there were minds discovering that the planets obeyed hidden laws, Galileo and the telescope. Then came the instrument that made the heavens intimate. Galileo did not invent the telescope, but he transformed it into an astronomical weapon. The Library of Congress notes that Galileo's telescopic observations dramatically changed how people understood the cosmos. When he saw mountains on the moon, he damaged the old belief in heavenly perfection. When he observed moons around Jupiter, he showed that not everything revolved around Earth. That was the beginning of a new kind of evidence, directed, technical, repeatable, and humiliating to old certainty. The moon was no longer an ideal glowing disk. It had topography, Jupiter was no longer a moving light alone. It had companions. Venus displayed phases that made better sense in a heliocentric framework. The heavens began to resemble a physical place with landscapes, systems, and bodies. This psychological change is essential to the later history of space exploration. Astronauts could be imagined only after the moon itself became imaginable as terrain. Craters make landings conceivable. Moons around Jupiter make other centers conceivable. Observed imperfection makes access conceivable. Galileo's telescope did not carry humans upward, but it brought the sky downward into inspection. And once the heavens could be inspected, they could be targeted. The sky had moved from mythic distance to technical proximity. Newton and the universal machine. Isaac Newton united earth and sky with one of the most important ideas in human history. The same gravity that pulls an apple downward governs the motion of the moon and planets above. The cosmos was not divided between corrupt earth below and perfect heaven above. It was a single physical system. That insight transformed space from sacred realm into engineering problem. Once gravity became universal, trajectories could be calculated. Once motion and force could be mathematically related, escape velocity became thinkable. Orbits were no longer mysterious loops in the sky. They were consequences of mass, velocity, and curvature. Newton mattered to later rockets for the same reason Kepler mattered. He made spaceflight legible. He turned cosmic motion into applied mechanics. There is a beautiful irony here. For thousands of years, human beings had looked upward and projected meaning onto the sky. Newton helped reverse the flow. The sky now explained the ground. One set of laws governed both. That is the true birth of astronautics in principle, not in fire, but in the realization that heaven and earth obey the same rules. Modern spacecraft are crude-looking descendants of a majestic intellectual event. Without Newton, no orbital insertion burn makes sense, no slingshot makes sense, no lunar return corridor makes sense. The first great bridge to space was invisible and mathematical. It was gravity understood. Observatories, navigation, and the age of precision. By the 17th century, astronomy had become tied closely to navigation, timekeeping, and state power. The Royal Observatory at Greenwich was founded in 1675, specifically to improve tables of heavenly motion and the positions of fixed stars so that longitude and navigation could be perfected. This is a wonderful turning point in the story. Space knowledge was now indispensable not only for philosophy or ritual, but for ships, empires, trade and war. The practical demand to know one's position on Earth strengthened the machinery of sky observation. From here, a longer pattern emerges. States fund astronomy when astronomy becomes useful. Later, states will fund rocketry when rockets become strategic. Then they will fund lunar missions when lunar missions become ideological, military adjacent, scientific or national in prestige. Greenwich and its siblings were not spaceports, but they were part of the same logic. Invest heavily in celestial knowledge because power flows from better control of position and time. Precision also changed the emotional tone of astronomy. The sky was still wondrous, but now it was also measurable to finer and finer degrees. Instruments grew, catalogues expanded, clocks improved. The universe was becoming a coordinated system of numbers. By the time rocket arrived, they would enter a world already trained to believe that exactness could conquer distance. Age of rockets fire. Arrows and the first artificial propulsion dreams. If astronomy provided the map to space, rocketry offered the first crude hint of movement toward it. Gunpowder rocketry has deep roots, especially in China, where early rockets emerged in military and pyrotechnic contexts long before anyone imagined orbital flight. These devices were not spacecraft, but they established the basic principle of reaction propulsion. Violent exhaust moving one way can throw an object the other. For centuries, rockets were mostly weapons, curiosities, or spectacle. They lacked the range, control, and efficiency needed for serious high-altitude or extra-atmospheric use. But ideas have long gestation periods. The same basic propulsion logic would eventually be refined into liquid-fueled launch vehicles capable of leaving Earth entirely. This is one of the recurring rhythms of technology. Play becomes warfare, warfare becomes industry, and industry becomes exploration. Spaceflight is filled with tools that began in more earthly and less noble circumstances. What is remarkable is how long the dream remained ahead of the reality. Human beings had the basic propulsion concept long before they had the materials, fuels, theory, or control systems to make it more than a flame-driven leap. Still, the seed was there. Something could propel itself without wings or sails. That mattered. The road to Saturn V began, in a distant ancestral sense, with sparks, tubes, and the first realization that fire could throw matter into the sky. The long 19th century of imagination. The industrial age expanded what human beings thought machines might do. Steam, rail, steel, electricity, and chemical engineering enlarged imagination. The possibility of leaving Earth remained absurd by practical standards, but it became imaginable in literature and serious speculation. This matters because history rarely advances through hardware alone. Imagination prepares institutions to tolerate radical ideas. By the late 19th century, questions once reserved for dreamers were beginning to attract theorists. Could a machine leave the atmosphere? Could propulsion work in a vacuum? Could people survive extreme altitude? Could rockets be staged? To later generations, these seem like technical questions. At the time, they were almost metaphysical. Space was still conceptually remote. Balloons could rise, but true departure from Earth remained closed. And yet the intellectual climate was changing. The Newtonian universe had made such journeys lawful in theory. Industrial modernity had made large machines psychologically ordinary. Science fiction and engineering were beginning to touch shoulders. The future pioneers of rocketry would emerge from this meeting place between imagination and mathematics. They would inherit old celestial knowledge and apply it to engines. The sky, once explained by priests and astronomers, was about to become the problem of the mechanics. 64 minutes. Tsiolkovsky and the mathematics of escape. Konstantin Tsiolkovsky, working in Russia in the late 19th and early 20th centuries, became one of the foundational theorists of astronautics. The National Air and Space Museum notes that he worked out how rockets could travel beyond the atmosphere. He understood a key constraint. Because rockets must carry their own propellant, their performance must be described mathematically in terms of mass and exhaust. Tsiolkovsky was a theorist more than a hardware builder, but theory is often the deepest engine. He imagined multi-stage rockets, space stations, and life beyond Earth at a time when all of these sounded impossibly distant. He is often remembered for a sentence later paraphrased endlessly in space history: "Earth is humanity's cradle, but one cannot remain in the cradle forever." That line endures because it compressed the whole project of space exploration into one emotional move. Space was not only a technical frontier, it was a stage in human maturation. Tsiolkovsky gave the movement its philosophical altitude. He told future engineers that leaving Earth was not fantasy but consequence. If Newton's laws were true, if enough velocity could be achieved, then escape was not forbidden. It was hard. The history of space exploration often depends on people who build machines. It also depends on people who make the impossible sound mathematically inevitable. Tsiolkovsky did exactly that. Goddard and the first liquid-fueled rocket, Robert H. Goddard, turned theory into fire. NASA and the Smithsonian both mark March 16, 1926, as a defining moment in modern rocketry. Goddard launched the first liquid-fueled rocket in Auburn, Massachusetts. Fueled by liquid oxygen and gasoline, it rose only briefly and not very high. But history is not measured only in altitude, it is measured in direction. Liquid fuel changed everything because it offered far greater promise for powerful, controllable propulsion than the earlier forms of rocketry. Goddard also worked on guidance, steering, and other technological foundations that later rockets would require. NASA calls him the father of modern rocket propulsion, and with good reason. What makes Goddard's story especially powerful is how modest the beginning looked. The first successful liquid fuel launch resembled a brief farm experiment more than the dawn of a cosmic era. It did not make headlines equivalent to its importance. Many people mocked or misunderstood his ambitions, but that little rocket was a hinge in time. It proved that propulsion suitable for the modern space age was possible. In retrospect, its scale seems almost poetic. One of the great shifts in civilization began with a machine that flew for seconds over snow. The future moon rockets were hidden inside that small and awkward flame. Oberth, rocket societies, and the culture of the future. If Tsiolkovsky gave astronautics its theory and Goddard gave it engineering credibility, Hermann Oberth helped energize a movement. The National Air and Space Museum notes that Oberth stressed the feasibility of a liquid propellant rockets for crewed flight into space and influenced a generation of enthusiasts and experimenters. Around these pioneers grew rocket societies and amateur professional communities. These groups mattered because they turned isolated brilliance into a field. Spaceflight had to become not just a dream but a discipline. That required clubs, demonstrations, journals, technical debates, and public campaigning. One of the recurring patterns in large technological revolutions is that they require subcultures before they require institutions. The rocket societies of the interwar years were exactly that. Small communities rehearsing a future that the mainstream still treated as eccentric. They also produced dangerous ambiguity. Rocketry was scientific. Rocketry was aspirational. Rocketry was also obviously military. The line between spaceflight and long-range weaponry was thin from the beginning. This double identity would define the 20th century. The same calculations that could one day send a probe to Mars could also send explosives across continents. The road to the moon and the road to the battlefield ran disturbingly close together. Space exploration would inherit both the grandeur and the stain of that fact. War and the V2. The Second World War forced rocket development into terrifying acceleration. Nazi Germany's V2 became the first long-range guided ballistic missile, and, in one sense, one of the machines that helped open the space age. The National Air and Space Museum notes that some historians date the space age to 1944, when a V2 reached space-like altitudes, though the more common symbolic beginning remains Sputnik in 1957. This is one of the central moral contradictions in the history of space exploration. Some of the technologies that later carried satellites and astronauts were sharpened first as engines of war. The V2 was technologically extraordinary and ethically inseparable from coercion, destruction, and the brutal system that produced it. After the war, both the United States and the Soviet Union moved quickly to capture German technology, hardware, documents, and personnel. The Air and Space Museum emphasizes that each side adapted V2 knowledge in the post-war years as military rocketry evolved into space launch capability. This is not a side note. It is the furnace in which the modern launch era was formed. Space exploration did not emerge from pure curiosity alone. It emerged from geopolitical fear, industrial mobilization, and military competition. The stars would be approached through a door blasted open by war. That does not cancel the wonder that followed, but it does complicate it forever. Post-war missiles, superpowers, and the new frontier. After 1945, the United States and the Soviet Union did not simply inherit rocket technology. They inherited a strategic obsession with range, speed, and deterrence. Intercontinental missiles and space launch vehicles would grow side by side. The Cold War intensified this process. Rocketry became a measure of national power. Could a nation launch farther, faster, heavier? Could it place something in orbit? Could it prove scientific and ideological superiority through the heavens? This is where space exploration becomes inescapably political. Agencies, laboratories, funding systems, and test ranges expanded because governments believed that mastery of the upper atmosphere and orbit was tied to military credibility and global prestige. And yet something else happened in parallel. Engineers, pilots, test specialists, and scientists began to imagine that these terrifying machines could be redirected toward more than deterrence. Missiles could become launchers. War platforms could become scientific instruments. That transformation is one of the most consequential acts of technological repurposing in history. The superpowers did not merely prepare for conflict, they accidentally built ladders to orbit. All that remained was for one of them to climb first. Space Age. To present. Sputnik and the night the sky changed. On October 4th, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. The achievement was technically modest by later standards and psychologically enormous by any standard. The sky was no longer purely natural. Humanity had placed an object into orbit. Sputnik was small, metallic and simple, yet its beeping signal announced that the age of speculation was over. We were in the space age now. Its effect on the world was electric. In the United States, it triggered alarm, education reform, institutional expansion, and intensified investment in science and technology. More broadly, it shattered an ancient boundary. For all of human history, nothing made by human hands had circled the planet from above. Then suddenly, something did. Space had become a theatre of proof. This is why Sputnik matters so much in cultural memory. It was not just first, it made the idea of global overhead real. The Earth could now be observed, crossed, and symbolically enclosed from above. Orbit itself entered public consciousness. The first satellite said something profound without words. Gravity can be negotiated. Earth can be departed, even if only partially. The atmosphere is not the final wall. The old sky belonged to nature. The new sky had traffic. Laika, Explorer, and the shock of competition Sputnik was quickly followed by deeper symbolic firsts. The Soviet Union launched Sputnik 2 and sent Laika into space, demonstrating that living creatures could survive launch, though tragically not return. The United States responded by intensifying its own efforts, and Explorer 1 became the first US satellite to successfully reach orbit in 1958. NASA itself was established that same year. It is difficult to overstate how compressed these years felt. Space milestones were arriving not once a generation but every few months. Each one felt like a referendum on national competence. Yet competition also accelerated knowledge. Life support, telemetry, launch reliability, tracking networks, and recovery concepts all advanced under the pressure of being second best. What the public saw as spectacular one-off victories were, beneath the surface, systems revolutions. This is one of the paradoxes of the space race. It was driven by rivalry, but it produced tools, data, and institutions that outlived the rivalry itself. The race also taught the world that exploration would not come cleanly. It would come with risk, propaganda, hero-making, secrecy, and trauma. The first living passengers in space were animals. The first crews would be test subjects as much as celebrated pioneers. The stars were drawing nearer, but the price of entry was becoming visible. Gagarin and the first human orbit. On April 12, 1961, Yuri Gagarin became the first human in space and the first human to orbit Earth. NASA's historical materials note that his single orbit mission kicked the space race into a much higher gear. The Air and Space Museum places him at the center of the early Soviet streak of firsts. Gagarin's flight was short, but that almost makes it more dramatic. A human being had left Earth, travelled around the planet, and returned alive. Millennia of skywatching culminated in a man inside a capsule falling forever around the world. The symbolic power was immense. The first person to actually see Earth from that vantage was not a philosopher or astronomer, but a military pilot strapped into a machine built by an industrial state. Human spaceflight had begun not as leisurely exploration, but as compressed test courage. Gagarin became a global icon because his mission joined fragility and transcendence. The capsule was small, the systems were experimental, yet the achievement felt civilizational. Human beings had entered the heavens in person. Everything after this point changes tone. Space is no longer only remote, it has been inhabited, however briefly. The ancient dream of ascent became a lived memory on April 12, 1961. Shepard, Glenn, and America learns to chase. Only weeks after Gagarin's orbital triumph, Alan Shepard became the first American in space on a suborbital Mercury flight. His mission was shorter and did not orbit, but it marked the United States' human entry into the contest. Then in 1962, John Glenn became the first American to orbit Earth. Project Mercury was America's first human spaceflight program. NASA summarizes it plainly: 6 crewed flights, 6 astronauts, and the creation of the first national generation of space heroes. Mercury introduced the United States not only to astronauts, but to the operational realities of human spaceflight: launch, stress, orbital systems, re-entry, splashdown, and recovery. Mercury's capsules were tiny. The astronauts were crammed into the very edge of what was survivable and barely workable. But that was the point. Mercury was not comfort. Mercury was proof. The psychological challenge for the United States was severe. The Soviet Union had reached orbit with first satellite, first animal, first human, and soon first woman. America needed not just a flight, but a strategy big enough to surpass the pattern. That strategy would come in a single political sentence from President Kennedy: send people to the moon and return them safely before the decade ended. The chase had found its destination. Tereshkova, Leonov, and the expanding human frontier. The Soviet Union continued its run of headline-grabbing firsts. In 1963, Valentina Tereshkova became the first woman in space. In 1965, Alexei Leonov performed the first spacewalk. These moments expanded what human spaceflight meant. Space was no longer a singular male pilot achievement. It was a widening frontier of human operation, endurance, and identity. Tereshkova's mission mattered for reasons far larger than propaganda, even though Cold War states used all such achievements symbolically. Space became a stage on which questions of who represents humanity began to surface. Not fully, not fairly, and not enough, but visibly. Leonov's spacewalk revealed something else. Living in orbit, it would require not only staying alive inside capsules, but working outside them. Extravehicular activity was dangerous and technically demanding. Space was hostile in practical ways that public celebrations could easily hide. The early years of human spaceflight often look triumphal in retrospect. They were also frighteningly experimental. Crews were testing the boundary conditions of human survival in vacuum, radiation-threatened environments, cramped vehicles, and minimally forgiving systems. Space exploration had moved beyond the question, can we get there? It was now asking, can we live and work there even for minutes? That question would define every station, every lunar landing, and every Mars concept that followed. Lunar and the first robotic reaches beyond Earth orbit. While human spaceflight captured headlines, robotic missions were making equally important breakthroughs. The Soviet lunar program achieved a series of major firsts: first impact on the moon, first images of the lunar far side, and early soft landing successes. Even before humans reached the moon, machines were scouting it. This is essential to remember because space exploration has always been a duet between people and robots. Crewed missions carry symbolism and immediacy. Robotic missions carry duration, daring, and range. They can go where humans cannot yet survive, and they often go first. Lunar robotic exploration changed the moon from a poetic object into a mapped operational target. The far side, invisible from Earth, was no longer abstraction once spacecraft photographed it, surfaced. Conditions became engineering concerns rather than imaginative guesswork. Here again, the old pattern repeats. Exploration becomes possible when mystery turns into terrain. Machines were preparing the moon for footsteps, just as later probes would prepare Mars for rovers and eventually human mission concepts. The robotic age did not follow the heroic age. It was there from the beginning, working quietly alongside it. In the long view, some of humanity's most powerful explorers never breathed at all. Gemini and the bridge to the moon. NASA's Gemini program was explicitly designed as a bridge between Mercury and Apollo. NASA describes it as the program that tested equipment and procedures in Earth orbit and trained astronauts and ground crews for future lunar missions. That bridge was crucial. Getting to the moon required much more than simply making capsules larger. Crews needed to learn rendezvous, docking, longer duration flight, orbital maneuvering, and extravehicular activity. Gemini taught these lessons under pressure and sometimes under crisis. Gemini 8, carrying Neil Armstrong and David Scott, completed the first docking in orbit before a dangerous spacecraft problem forced an emergency return. NASA's summary of the mission captures the dual tone of Gemini perfectly: accomplishment and peril in the same breath. This is often how frontiers work. The glamorous milestone depends on a less glamorous apprenticeship. Gemini was apprenticeship at high speed. If Mercury asked whether humans could survive space, Gemini asked whether they could operate there with enough precision to reach the moon. The answer by the end of the program was yes, barely, impressively, and with growing confidence. Apollo would inherit not just hardware lessons, but a new kind of professional composure. Spaceflight was becoming a practiced craft, not merely a gamble. Apollo 1 and the cost of ambition. The race to the moon was not a clean ascent. In January 1967, A cabin fire during a ground test killed astronauts Gus Grissom, Ed White, and Roger Chaffee. The disaster forced a painful rethinking of design, safety culture, and program urgency. Space exploration histories often risk smoothing tragedy into montage. They should not. Apollo 1 was a warning written in flame. Engineering ambition can outrun caution. Symbolic pressure can hide systemic weakness. NASA's later Apollo histories make clear how central this turning point was. The command module had to be redesigned. Procedures changed. The program paused, examined itself, and rebuilt. When Apollo flew again, it did so with sharper humility. This pattern would repeat across space history. Challenger, Columbia, Soyuz losses, every mature spacefaring culture eventually learns the same lesson. The margin between triumph and catastrophe is often terrifyingly small. Yet tragedies also reshape institutions. Apollo 1 made later successes more solid because it forced reality into a program driven by deadline and prestige. The moon would not be reached by determination alone. It would require ruthless respect for detail. Human space exploration has always had martyrs. Apollo 1 stands near the front of that solemn line. 116 Apollo 8 and the first departure from Earth. In December 1968, Apollo 8 became the first crewed mission to leave Earth orbit, travel to the moon, circle it, and return. That sentence alone still feels impossible. A species that had begun by drawing constellations in stories had now physically departed its home world. Apollo 8 changed the human perspective not only through navigation, but through imagery. The mission's famous Earth view photographs made the planet appear small, luminous, finite, and shared. People had always known Earth was one world. Apollo 8 made that knowledge emotional. This is one of the great secondary effects of space exploration. The missions go outward, but they change how humanity sees inward. Earth from deep space looks borderless and fragile. Environmental consciousness, global imagination, and planetary politics were all quietly altered by that visual fact. Apollo 8 was also a rehearsal in the deepest sense. It proved that mission control, translunar navigation, re-entry and crew performance could function on a scale beyond low Earth orbit. Humanity had now practiced deep space travel. The moon was no longer merely observable, photographable, or orbitable by machines. It had been visited by human voices, and now, after generations of thought and a furious decade of engineering, only one step remained. Landing, Apollo 11 and the first footprints Apollo 11 launched on July 16, 1969. Its stated mission objective, as NASA summarizes it, was to fulfill Kennedy's goal, perform a crewed lunar landing and return safely to Earth. 4 days later, Neil Armstrong and Buzz Aldrin landed in the lunar module, while Michael Collins remained in orbit. Armstrong became the first human to step onto the moon. The event is so familiar that it risks becoming abstract. It should not. A human being climbed down a ladder onto another world. The mechanics were exquisite, the danger real, the symbolism overwhelming. Navigation errors, fuel limits, descent uncertainty, communications delay, suit design, ascent reliability. Everything had to work well enough in sequence. And it did. Apollo 11 changed space exploration from possibility into precedent. After July 1969, the question was no longer whether humans could walk on another celestial body. It was whether they would do it often and what they would do next. The first landing also marked the peak of a particular kind of explorative drama. National, televised, heroic, centralized, and Cold War framed. Everything afterward would be measured against it. The dust accepted the bootprint. Humanity had crossed its oldest imagined threshold. Beyond the first step, Apollo did not end with Apollo 11. Several more lunar missions followed, each extending the complexity and scientific seriousness of surface exploration. Crews stayed longer, drove farther, and collected more geology. If Apollo 11 was proof, the later missions were fieldwork. This is important because exploration matures by becoming less ceremonial. Once firstness passes, operations begin. The moon shifted from spectacle to research site. Astronauts learned to work there, not just stand there. Apollo also left unfinished business. The moon was reached 6 times by crews, but the long-term infrastructure many had imagined never followed. Budgets changed, politics shifted, public attention moved. The dream of regular lunar presence faded. This has shaped every later generation of space policy. Apollo remains both benchmark and burden. It proved astonishing capability while also making any lower level of ambition look like retreat. In the public imagination, the moon landing was supposed to be the beginning of an even larger future. In reality, it became a summit followed by a long plateau, but summits matter. They redefined the conceivable, and once human beings had stood on the moon, no later frontier could claim to be entirely absurd. Mars, stations, asteroids, and outer planets all became easier to imagine in an Apollo-made world. 128 minutes. Salyut, Skylab, and learning to stay after the moon race. Another question rose to the foreground. Not how to reach a place briefly, but how to remain in space for long periods. Space stations became the answer. The Soviet Salyut stations, and later Mir, focused heavily on long-duration human presence. The United States launched Skylab in the 1970s, proving that crews could inhabit, repair, experiment, and adapt to orbital living for extended missions. The logic of exploration had shifted from voyage to occupation. This was a profound transition. The first era of human spaceflight was about crossing thresholds. The second was about endurance. How does the body change in microgravity? How do people sleep, eat, exercise, repair equipment, and maintain morale in orbit? These are not or glamorous questions, but without them there is no moon base, no Mars expedition, no serious future beyond brief flags and footprint sorties. Space stations taught humanity how difficult normal life becomes off Earth. Everything must be managed: air, water, waste, muscle, bone, irritation, attention. Orbit is survivable, but never casually. The station era also revealed something bigger. Exploration is not only about going outward, it is about building systems that let fragile biological beings remain operational in hostile environments. In that sense, every station is a small civilization module. Shuttle and the promise of reuse. When the Space Shuttle first flew on April 12, 1981, exactly 20 years after Gagarin's mission, NASA introduced a radically different model of human spaceflight. The shuttle was the world's first reusable spacecraft and could carry large satellites to and from orbit while launching like a rocket and landing like an airplane. NASA marks STS-1 as the beginning of a 30-year shuttle era. The shuttle embodied a new hope that space access could become more routine, more flexible, and more operationally rich. Crews could deploy payloads, conduct research, repair satellites, build infrastructure, and return with cargo. The spacecraft itself looked less like a capsule of survival and more like a versatile orbital truck. In practice, the shuttle was brilliant, complicated, and never as cheap or routine as its more optimistic early vision suggested. But its real historical importance lies elsewhere. It expanded what a crewed space mission could do. The shuttle era also broadened who went to space. NASA notes that it opened flight opportunities more widely and helped shape a more socially varied astronaut corps over time. If Apollo was a spear to the moon, the shuttle was a toolkit in orbit. Its missions were less singularly mythic, but often more functionally rich. The future of orbital construction and servicing depended on that shift. Challenger, Columbia, and the end of innocence again. The shuttle also exposed the recurring vulnerability of human spaceflight. Challenger was lost in 1986. Columbia was lost in 2003. Between those disasters and the triumphs of the program lies the permanent truth of crewed exploration. Technological sophistication does not erase fragility. The emotional force of these losses came partly from the shuttle's public familiarity. Because shuttle missions seemed more regular, some people imagined the risk had been domesticated. Disaster shattered that illusion. Space history repeatedly cycles through confidence and correction. Systems begin to look dependable. Institutions normalize risk. catastrophe reminds them that off-world operations remain harsh, unforgiving, and intolerant of small failures multiplied. The consequences of these accidents were technical, managerial, and cultural. Investigations produced changes in oversight, engineering review, mission rules, and organizational behavior. More deeply, they forced public audiences to confront the fact that human space exploration would never become risk-free in the way commercial air travel became familiar. Every age of exploration develops myths of mastery. Space has a habit of breaking them, and still the missions continue. That continued will after tragedy, after investigation, after grief, is part of the story too. The desire to go does not disappear because the path is dangerous. If anything, history suggests that danger only clarifies how much the frontier matters to those drawn toward it. Hubble and the machine that could be repaired. In 1990, the Hubble Space Telescope launched into orbit. Soon after, a flaw in its primary mirror damaged the clarity of its early images. This could have turned Hubble into a very expensive disappointment. Instead, became one of the greatest comeback stories in scientific history. NASA designed Hubble to be serviced in orbit, and 5 shuttle servicing missions upgraded and repaired the observatory over time. That design choice changed scientific history. Servicing missions turned Hubble from a troubled observatory into a continuously renewed instrument at the cutting edge of astronomy. NASA later described the final servicing mission as a rebirth, and that is not exaggeration. Hubble matters in the history of space exploration because it shows that exploration is not only travel, it is sight. It is the expansion of perception. Hubble changed our view of starbirth, galaxies, deep cosmic time, and the scale of the universe. It made space emotionally visible to billions of people. In another sense, Hubble was a monument to partnership between humans and machines. Astronauts physically repaired the eye that then transformed all human seeing. This is one of the most moving loops in space history. We go into space partly to build better ways of looking deeper into space. The explorer and the instrument keep upgrading each other. Station Earth. The International Space Station became the fullest realization of the station idea. NASA describes it as a laboratory, classroom, and proving ground orbiting about 250 miles above Earth at roughly 17,500 miles per hour. It has hosted nearly 300 astronauts and supported thousands of experiments. ESA notes that Columbus became Europe's first permanent research facility in space when attached to the station in 2008. Beyond its science, ISS mattered because it redefined what space power could look like after the most intense Cold War competition. Former rivals became partners. Americans, Russians, Europeans, Japanese, Canadians, and later commercial providers, and has contributed to a living multinational outpost. That cooperation does not erase geopolitics, but it demonstrates something vital. Orbit can also be a domain of shared operation. Life aboard the ISS is both mundane and extraordinary. Exercise machines, sleeping quarters, maintenance routines, windows, laptops, research racks. Ordinary tools in an extraordinary environment. The station transformed being in space from brief expedition to ongoing habitation. It also became a training ground for the next frontier. NASA repeatedly frames the ISS as preparation for future lunar and Mars missions. In that sense, the station is not an endpoint. It is a rehearsal for deeper absence from Earth. A house in the sky turned into a school for the farther dark. Venus, Mars, and the robotic vanguards. While crews learned to stay in orbit, robots expanded the reach of exploration far beyond it. NASA's early planetary missions to Venus and Mars were the first attempts to move space exploration into true interplanetary science. Mariner 2 became the first successful mission to another planet, Venus, and later Mariner missions went outward to Mars. JPL describes Mariner 4's 1965 flyby of Mars as the moment when grainy black and white close-ups began changing human understanding of the planet. For centuries, Mars had been a red point loaded with speculation. Now it had a face. This is a recurring emotional moment in robotic exploration. A world changes category the instant it is imaged up close. Venus stopped being merely brilliant. Mars stopped being merely suggestive. They became places with surfaces, storms, craters, chemistry, and operational questions. Robotic missions also revealed that the imagination is often wrong in detail. Mars had once been romanticised with canals and civilizations. Mariners' images instead showed a harsher, older, cratered world. Exploration means correction as much as discovery. From this point onward, every serious dream of human Mars exploration would be built on the shoulders of machines that arrived first in disappointed fantasy into reality. That is one of exploration's noblest functions. It teaches us to love the truth, even when it is less flattering than the myth. Viking and the first search for life on Mars. The Viking missions of the mid-1970s marked a giant leap for planetary science. NASA describes Viking 1 as the first spacecraft to successfully land on Mars, and emphasises that the mission was designed not only for imaging and atmospheric study, but also to search for signs of life. NASA's astrobiology materials could again similarly identify Viking as the first mission to reach the Martian surface and the first to search there for evidence of life. What Viking discovered was complex. It did not give humanity a simple yes, but it transformed Mars from a speculative target into a laboratory world. The surface could be tasted by instruments, soil could be tested, weather could be watched. This matters because astrobiology changed the moral weight of exploration. Space was no longer only about engineering glory or national prestige. It became a search for context. Is life common? Is Earth unusual? Did Mars once host environments suitable for microbes? Those questions do not feel like Cold War questions. They feel older and deeper. Viking helped broaden the purpose of exploration from geopolitical demonstration to planetary inquiry. Mars became not just a place to reach, but a place to interrogate, and the absence of easy answers only sharpened the fascination. A world that does not reveal itself quickly becomes even more compelling. Pioneer, Voyager, and the Grand Tour. If Mars brought exploration emotionally close, the outer planets made it epic again. NASA's exploration history notes that Pioneer 10 and 11 made the agency's first visits to Jupiter and Saturn, while Voyager 1 and 2 followed with even richer observations. Voyager 2 later became the first spacecraft to fly by Uranus and Neptune. The Voyagers in particular redefined scale. Launched in 1977, they used a rare planetary alignment to conduct a grand tour of the outer solar system. They revealed active volcanoes on Io, unveiled the complexity of Jupiter and Saturn, and gave humanity its first close-up looks at Uranus and Neptune. NASA describes Voyager 1 as the farthest human-made object still moving outward today. The mission also carried the Golden Record, a curated message from Earth in multiple languages and sounds, a striking fusion of science, hope, and symbolism. NASA and JPL describe it as a greeting to possible distant listeners, even if the odds of encounter are vanishingly small. Voyager changed the geography of imagination. The solar system was no longer an artist's guess. It was filmed, measured, radioed home. These probes made distance emotionally navigable. They let ordinary people become familiar with giant storms, ring systems, and ice worlds they would never personally visit. Exploration became cosmic tourism through instrumentation. Galileo, Cassini, and the deep planetary age. After the flyby era came the age of orbiters and long-term planetary residents. Missions no longer just passed worlds, they stayed with them. At Jupiter, missions built on the path opened by Pioneer and Voyager. At Saturn, the Cassini-Huygens mission became one of the masterpieces of international planetary exploration. JPL's press materials described Cassini as the most highly instrumented and scientifically capable planetary spacecraft yet flown at the time, with the orbiter carrying 12 instruments and the Huygens probe adding 6 more through the NASA-ESA partnership. Huygens' descent to Titan in 2005 gave humanity a landing on a distant moon wrapped in thick atmosphere. Titan stopped being only mysterious haze. It became a place with rivers, methane weather, and a surface that could actually receive a machine from Earth. This is another great trend in exploration history. Familiarity keeps outrunning imagination. Once a remote world becomes a long-term mission site, it ceases to be just remote. Deep planetary missions also changed to timescales. The public had to learn patience. Some spacecraft took years to arrive and then years more to reveal their richest results. Exploration became extended conversation rather than single dramatic event. The solar system was learning to keep our machines for decades. Comets, asteroids, and the small body revolution. not all dramatic exploration targets are planets. Small bodies, comets and asteroids, carry clues to the solar system's formation and chemistry. ESA's Rosetta mission achieved several historic firsts. First rendezvous with a comet, first to follow one along its orbit around the Sun, and first to deploy a lander to a comet's surface. Rosetta mattered scientifically, but it also mattered narratively. For the first time, the public could experience a mission that did not just inspect a comet in passing, but accompanied it through changing sunlight and activity. The old image of a comet as distant omen was replaced by a detailed, evolving world. Japan's Hayabusa 2 added another landmark by returning samples from asteroid Ryugu, and, as JAXA reported, even returning gaseous components, the first time that had been achieved from a near-Earth asteroid mission. Hayabusa 2 continues on an extended mission toward additional targets. These missions widened the meaning of exploration again. Space was not only about giant destinations, it was also about primitive rubble, chemical history, and the building blocks of planets and life. Sometimes the smallest worlds carry the oldest stories. Robotic exploration learned to read them. Mars Pathfinder and the return of surface mobility. After Viking, Mars exploration paused and then reawakened in new forms. Mars Pathfinder and its tiny rover Sojourner helped reintroduce the idea that Mars was not just a landing site, but a traversable landscape. The mission was technologically lighter and more experimental than Viking, but it restored momentum and public affection for robotic Mars science. There is something emotionally important about rovers. Landers feel like visits. Rovers feel like travelers. The moment wheels touch another world, the planet becomes a space of route, choice, and encounter. Pathfinder's success also reminded everyone that exploration could be charming as well as grand. Tiny rovers moving among rocks and sending back images made Mars feel companionable. A machine could wander there. That changed the texture of public imagination. Space history is full of giant engineering monuments, but some of its most beloved emissaries are small. They embody persistence. They resemble field scientists more than conquerors. That sensibility would only grow stronger with the Mars exploration rovers that followed. Mars was becoming, mission by mission, the most inhabited, uninhabited world in our imagination. Spirit, opportunity, and the long walks on Mars. The twin Mars exploration rovers, Spirit and Opportunity, extended everything. Pathfinder had promised. Designed for far shorter durations, they far outlived expectations and turned the Martian surface into a place of long-term geological fieldwork. Opportunity in particular became legendary for endurance. These rovers did more than transmit science. They generated attachment. People followed their routes, their setbacks, their views, and their improbable survival through dust, terrain, and time. This is a distinctive feature of robotic exploration in the modern age. Personhood gets projected onto machines, not because people are naive, but because the machines become the only moving representatives of humanity in places no human has reached. They are lonely on our behalf. The rovers also strengthened the evidence that Mars had once hosted liquid water environments. The planet's past grew more habitable as the data accumulated. Mars stopped looking merely dead. It began to look historically alive in possibility, even if not conclusively in biology. By the time Spirit fell silent and Opportunity later succumbed, the story of Mars was no longer one of occasional glimpses. It was a living archive of years on the ground. The robot field geologist had become one of the defining characters of space exploration. Curiosity and the habitability question. Curiosity, launched in 2011 and landed in 2012, brought a much larger and more capable rover to Mars. NASA states that Curiosity's mission is to investigate whether Mars was ever habitable to microbial life. This marked a clear evolution in exploratory intent, from searching vaguely for life to assessing habitability in environmental detail. Curiosity's landing itself was a technological statement. The Sky Crane descent system looked almost absurdly ambitious, and then it worked. As so often in space history, success instantly turns the outrageous into procedure. The rover has since operated as a mobile chemistry and geology lab, analysing ancient environments and helping reconstruct the deep environmental history of Mars. That long continuity matters. On Mars, each active rover extends human presence symbolically. It becomes a standing conversation with another planet. Curiosity also belongs to a broader historical shift. Exploration guided increasingly by questions of origin and context. Was Mars once wet? Was it stable enough for life? How different did planets need to be to diverge so dramatically from Earth? These are profound questions, and curiosity helped anchor them in sediment, mineralogy, and field science rather than pure speculation. Mars was not getting simpler, it was getting more interesting. Perseverance, samples, and the dream of return. Perseverance, which launched in 2020 and landed in Jezero Crater in 2021, was built to search for signs of ancient microbial life and collect rock and regolith samples for possible return to Earth. NASA frames the Mars 2020 mission as the first step of a proposed round-trip campaign to bring carefully selected Martian samples home. This is a major conceptual step. For decades, planetary science meant sending instruments to where the rocks are. Sample return reverses the logic. Bring the rocks to the best laboratories on Earth. That reversal is extraordinarily difficult. It implies a chain of missions, orbital rendezvous around another planet, sterile handling, and years of planning. NASA's Mars sample return concept remains one of the most ambitious robotic campaigns ever attempted, even as the agency continues to reassess cost, risk, and architecture. Perseverance also carried Ingenuity, the small helicopter that proved powered flight on another planet. Even though its role was experimental, the meaning was enormous. Another world now had its own local aviation history. Jezero Crater became many things at once: an ancient lake bed, an astrobiological target, a sampling ground, and the first airport in Martian history. Space exploration keeps doing this, turning distant abstractions into places with absurdly specific firsts. Space telescopes and the expanding window, space exploration, is not limited to moving through the solar system. Some of its greatest achievements come from placing observatories beyond Earth's atmospheric distortion. Hubble defined this model for decades, and in 2021 the James Webb Space Telescope extended it dramatically. NASA describes Webb as an infrared observatory that studies every phase in the history of the universe, from the earliest luminous structures after the Big Bang to the formation of solar systems. It launched on December 25, 2021, and now operates around the Sun near the second Lagrange point, about 1.5 million kilometers from Earth. Webb matters in the history of exploration because it stretches the definition of frontier. Some frontiers are spatial in the sense of where a spacecraft goes, others are temporal in the sense of how far back an instrument can see. Webb is both. It is physically distant and historically deep, looking toward early cosmic history while also studying nearby exoplanets and star-forming regions. The explorer here is not a crew or rover, but an eye, cold, shielded, precisely aligned and patient. Space exploration, at its grandest, is a contest against ignorance in every direction. Inward to the atom, outward to the galaxy, backwards to the beginning sun, forward to possible futures. Webb extends the human window. That too is a way of travelling, 188 into China, India, Japan, and the multipolar space age. For much of the 20th century, people often narrated space history as a US-Soviet duel. In the 21st century, that picture is no longer enough. China's Chang'e program achieved a historic first when Chang'e 4 made the first soft landing on the far side of the moon in 2019. In 2024, Chang'e 6 returned the world's first samples from the lunar far side. These were not symbolic gestures. They were major scientific and operational milestones in lunar exploration. India's Chandrayaan-3, which ISRO describes as a mission to demonstrate end-to-end safe landing and roving capability on the lunar surface, marked another important moment in the democratization of lunar access. Japan's Hayabusa 2, meanwhile, showed how sample return exploration could be pursued with extraordinary precision and long-term planning. JAXA continues to extend the mission's life toward additional asteroid encounters. This multipolar age changes the story. Space is no longer shaped only by two superpowers and their legacy institutions. It is increasingly a field of many states, many agency cultures, many goals, and many pathways to prestige or science. The sky is getting crowded with ambition. Commercial crew and the return of orbital launches from the United States. The rise of private industry transformed another part of the space story. NASA's Commercial Crew program was designed to deliver safe, reliable, and cost-effective transport to and from the International Space Station through partnerships with industry. NASA identifies the SpaceX Crew Dragon system as a certified vehicle under this program, with regular operational missions now taking astronauts to orbit. The significance of this shift is not just financial or contractual, it changes the institutional architecture of exploration. Rather than owning every crew transportation system directly, NASA increasingly acts as partner, customer, and architect of ecosystems. This is a major evolution from the fully state-built model of Mercury, Gemini, Apollo, and Shuttle. It does not mean governments become irrelevant. It means the frontier acquires a mixed economy. Commercial Crew also restored a capability that had lapsed after shuttle retirement, launching astronauts to orbit from US soil. That restoration had symbolic value as well as operational value. Meanwhile, companies like Blue Origin have pushed reusable suborbital human spaceflight. Blue Origin describes New Shepard as a fully reusable suborbital system built for human flight from the beginning, carrying passengers past the Kármán line for several minutes of weightlessness. The commercial turn is not the end of state exploration. It is a new layer added on top of it. Reusability and the new economics of access. One of the most important contemporary changes in spaceflight is the drive toward reusability. The shuttle embodied an early and partial version of that dream, but the modern commercial era has pursued it more aggressively with vertically landing boosters and reusable architectures. Blue Origin explicitly frames reusability as the key to radically reducing the cost of access up to space and notes that both New Shepard and New Glenn were designed around that principle. NASA's current commercial and Artemis frameworks likewise assume a much larger role for industry in launch, logistics, and landing systems. Why does this matter historically? Because the expansion of exploration has always been constrained by cost and cadence. If launch remains rare and ruinously expensive, exploration remains exceptional. If launch becomes more repeatable and affordable, new categories of mission become thinkable. This does not mean space suddenly becomes easy. It means the economics may begin to shift from singular prestige missions towards sustained architectures. We are still early in that transition, and hype often exceeds delivered reality, but the direction is unmistakable. The future of lunar logistics, station resupply, commercial science, possible tourism, and eventually deeper space industrial systems depends heavily on whether access can become more routine. The dream of a spacefaring civilization has always been partly an engineering dream and partly a cost curve dream. Reusability is where those two meet. Artemis and the return to the Moon. NASA's Artemis campaign is the clearest current attempt to restore deep space human exploration beyond low Earth orbit. Artemis 1 flew uncrewed in 2022. Artemis 2, according to NASA's official mission page, flew in April 2026 as the first crewed lunar flyby of the Artemis era, carrying astronauts farther from Earth than any humans had gone in more than half a century. NASA's broader Artemis material frames the program as a path to the Moon that also builds toward Mars. The meaning of Artemis is layered. On one level, it is return humans back to the vicinity of the Moon after decades. On another, it is redesign. Not Apollo repeated, but a new architecture involving Orion, the Space Launch System, commercial landing systems, international partners, and eventually Gateway in lunar orbit. NASA's current planning signals Artemis 3 for 2027 and a broader sequence of missions, though the exact path remains shaped by development and testing. That uncertainty is normal. Space exploration is always planned in crisp diagrams and executed in a messier reality. Still, Artemis marks a strategic truth. The Moon is no longer remembered only as a place once visited. It is again being treated as a future operational zone. History had looped back to the old silver target, but with very different tools: gateway landers and building an architecture. A major difference between Apollo and the current lunar renaissance is architecture. NASA's Gateway program envisions a small station around the Moon, built with international and industry partners, to support lunar surface missions and help chart a path toward Mars. NASA describes it as humanity's first space station around the Moon. The human landing system sits inside this architecture. NASA identifies it as the transportation mode that will carry astronauts from lunar orbit to the surface and back. The current HLS framework includes SpaceX for Artemis 3 and 4 and Blue Origin for Artemis 5. These programs reveal a fundamental change in exploratory style. The goal is no longer one dramatic visit followed by retreat. It is a network. Launch vehicles, deep space capsules, orbital nodes, lunar landers, logistics, science payloads, and eventually surface systems. NASA's CLPS program reinforces this by using commercial lunar delivery services to send science and technology payloads ahead of or alongside future crews. In other words, the Moon is being approached as an ecosystem, not a one-off destination. This is how frontiers become settled in operational terms, not by one heroic act, but by supply chains, modular hardware, regular cadence, and mixed participants. The Moon is re-entering history not simply as a symbol, but as infrastructure. Mars dreams, sample return, and the next great leap. Mars remains the great outward magnet of modern human exploration. NASA presents Moon to Mars as a linked strategy. Return to the Moon, develop systems in deep space, and use those lessons to prepare for eventual human missions to Mars. But Mars is not only a human dream, it is also a robotic campaign still unfolding. Mars sample return would, if realized, bring carefully selected Martian material to Earth for the first time. NASA describes it as potentially the most ambitious multi-mission planetary campaign ever attempted, though the program has also faced serious reassessment over architecture, complexity and cost. ESA's ExoMars program also remains part of this future landscape. ESA states that the Rosalind Franklin rover now targets launch in 2028, with the mission focused on whether life has ever existed on Mars. NASA and ESA have further coordinated on support for the mission. Mars then stands as both near future ambition and slow, stubborn engineering problem. It is close enough to organise around, far enough to resist simple slogans. Every era of space history seems to need one destination that is both plausible and intimidating. For our era, that destination is Mars. Law, ownership, and the problem of who space is for. As exploration expands, so do political and ethical questions. The 1967 Outer Space Treaty remains the cornerstone of international space law. UNOOSA notes that it establishes outer space as a domain to be carried out for the benefit and in the interests of all countries, and that outer space and celestial bodies are free for exploration and use by all states without discrimination. It also addresses peace, cooperation, and responsibility. This treaty language is noble and still profoundly relevant, yet modern space activity makes it harder to interpret. What does province of all mankind mean when access is highly unequal? How should commercial resource use be framed? Who bears responsibility for dead satellites, collision risk, or private actors operating under national licenses? These are not abstract legal puzzles. They shape the future of lunar mining proposals, seize lunar traffic, orbital management, and the legitimacy of commercial expansion. Space exploration began under myths of gods and kings, then passed into the hands of empires and superpowers, and now increasingly includes corporations. The question of who the sky belongs to has never disappeared. It has only changed forums. The future frontier will not be shaped by propulsion alone. It will be shaped by legal imagination and political compromise. Debris, sustainability, and not ruining orbit humanity has now placed so much material into orbit that sustainability itself has become a frontier problem. UNOOSA and ESA warn that space debris poses a clear risk to the long-term sustainability of outer space activities. The United Nations also adopted guidelines on the long-term sustainability of outer space activities in 2019, emphasizing policy, safety, cooperation, and technical development. This is a very modern kind of exploration crisis. Earlier ages worried about whether the frontier could be reached. We now worry about whether we will clutter it so badly that access becomes harder and more dangerous. Debris is the refuse side of transcendence. Every explosion of fragment, dead satellite, and abandoned upper stage reminds us that exploration scales waste unless governed carefully. The problem is especially revealing because it forces civilization to mature. A species serious about becoming spacefaring cannot behave in orbit the way it once behaved on frontiers treated as endless. Near-Earth space is not endless in operational terms. It is crowded, useful and vulnerable. Sustainability is therefore not separate from exploration. It is one of its conditions. To explore well is not only to arrive, it is to preserve the domain so others can follow. Planetary protection and the ethics of contact. There is another ethical boundary: contamination. NASA's Office of Planetary Protection defines planetary protection as the practice of protecting solar system bodies from contamination by Earth life and protecting Earth from possible life forms that may be returned. The goal is responsible exploration that protects science, environments, and our own biosphere. This matters more as missions become more ambitious. Sending a lander to Mars is one thing, sending humans is another. Human beings shed biology everywhere. If Mars ever held or still holds life, then exploration could also become interference. Planetary protection asks a deceptively simple question. How do you investigate another world without erasing the very evidence you seek? The issue reaches beyond Mars. It applies to icy moons, sample return missions, and any serious future in which off-world operations become more common. The old heroic image of exploration as simple arrival is no longer enough. Responsible exploration now includes restraint. This is one of the deepest signs that space history has matured. We no longer imagine the frontier as empty by default. We now approach some worlds as scientifically delicate places whose integrity matters independently of our desire to reach them. Curiosity brought us to the threshold. Ethics tells us how to cross it. Why humans keep going. At every stage of this history, critics have asked the same question in different forms. Why go? Why spend so much to leave Earth when Earth itself remains wounded, unequal, and unfinished? The answer has never been singular. Space exploration produces science. It drives engineering and computing. It yields Earth observation, communication, navigation, materials knowledge, and medicine. It trains nations and institutions. It inspires education. It satisfies curiosity. It also gives human beings a larger frame in which to see themselves. NASA explicitly presents the ISS as yielding advances in medicine, material science, climate research, and technologies relevant to future exploration. But beneath all the practical arguments lies something older. Human beings are a horizon species. We test edges. We tell stories about the unknown, then build tools to step into it. Space is the largest expression of that trait. The danger, of course, is confusing expansion with virtue. Exploration is not automatically noble. History on Earth proves that. It must be directed, governed, and morally examined. Yet the impulse itself, the desire to know what lies beyond the ridge, is inseparable from our species' story. The sky called to ancient shepherds, priests, sailors, and astronomers. Now it calls to engineers, roboticists, and crews. The voice is the same, the means have changed. Closing reflection. The complete history of space exploration is not simply a history of moving upward. It is a history of changing scale. A species once bounded by valleys learned to think in continents, then in oceans, then in planets, then in solar systems. Every age believed it understood the sky well enough until a new instrument, a new theory, or a new machine proved otherwise. Ancient observers learned that the heavens had patterns. Greek and Islamic astronomers helped turn those patterns into models. Renaissance thinkers broke Earth from the center. Rocket pioneers proved escape could be engineered. Empires and superpowers militarized the path. Then astronauts, probes, and telescopes filled that path with footprints, signals, images, laboratories, and messages to the unknown. Today, orbit is busy. The moon is back in planning documents. Mars is no longer fantasy, only difficulty. Telescopes read ancient light. Robots roam red dust. Laws strain to keep up. Debris circles overhead. Private vehicles launch beside state programs. The frontier is no longer singular. It is scientific, commercial, legal, philosophical, and moral at once. And still, the oldest image remains the most powerful. a human being standing under the night sky, looking up. What changed is that now, somewhere in that darkness, there are machines carrying our instruments, our voices, our mathematics, our laws, our mistakes, and our hope. The first skywatchers could not have known that one day humans would leave Earth, orbit it, walk on the moon, build laboratories in the void, fly helicopters on Mars, land on the far side of the moon through relay satellites, and plan new journeys back to deep space. But they did know one thing that still remains true. The sky is not signless. It isn't her. And human history again and again has been the story of answering. On-camera channel intro. Script. Hey everyone! Welcome to the channel. Here we explore the rise of civilizations, the history of empires, the story of science, and the breakthroughs that changed the world. Our goal is to turn massive historical subjects into clear, cinematic, long-form documentaries you can sit with, learn from, and experience from beginning to end. If that sounds like your kind of journey, you're in the right place.